Physics students, good afternoon. Mr. Fugit here. In this problem, we're going to be looking at another kind of a circular motion scenario for an object moving in a horizontal circle, but we'll be kind of applying our understanding of circular motion to solve for something a little bit different than we did previously, solving for a force. In this problem, specifically, we're going to be looking at finding the maximum amount of tension that a string can hold before it begins to break. So this is going to be geared more specifically towards problem number 5 on your most recent homework assignment 7 that covers over circular motion and universal gravitation. So I'll read the problem statement for us and then we will get started. It says this: a string under a tension of 48 newtons is used to whirl a rock in a horizontal circle of radius 3.3 meters at a speed of 32.17 meters per second. The string is pulled in and the speed of the rock increases. Okay? When the string is 0.717 meters, our radius is going down, and the speed of the rock is 59.1 meters per second, the string breaks. What is the breaking strength of the string? So this question is really asking us, what's the maximum amount of tension this string can hold? Is we're going to decrease our radius and speed up our object, and it's going to cause the string to break. So if we're dealing with an object moving in a circle, remember, we can characterize the force that's causing it to do that as a centripetal force. So, geared more towards problem number 5. If we take kind of a side view of what's happening here, we're moving in a horizontal circle. So that would mean, from a side view, gravity's acting downward, Fg, and we have a tension force directed inward toward the center of the circle. That would be our centripetal force here. So when it's asking us for a tension force, we can treat that as a centripetal force, which we have an equation to be able to calculate. So because our force of gravity is not really affecting our movement toward the center, we don't really need to factor it into this scenario. Excuse me. So now in this problem, there are kind of 2 different scenarios we're given, right? Tension value for the string at the beginning, and then we're changing some of the values that's going to cause our tension to go up and eventually break. So, to find that breaking tension, we're going to treat Ft as our centripetal force. And so to find that tension force, we'll set our tension force equal to mv squared over r. Now, if this is going to be our scenario when the string is going to break, we have some information specifically about the values that cause our string to break. And we know that at that point, we're moving at a velocity equal to, my value is 59.1 meters per second, which, as you all know, is extremely fast. And that our radius is a small value, smaller than it was, of 0.717 meters. Now, as you'll probably recognize, there's something missing that's going to prevent us from solving this problem as it's given to us. And you'll notice we're missing the mass that's needed to find that tension force. However, we're also given some information previously, when we are spinning this rock at a different, kind of a different amount of tension, a different velocity, a different radius of our circle. And what we're going to do is we're going to use that initial information to solve for that mass, because even though we might change the speed we're rotating at, we might change the radius of our circle, make it smaller, the mass of that rock isn't going to change. It's going to be the same in both scenarios. So what I'm going to do is I'm going to look at those previous conditions. Right? I'm going to use those to try and find our mass. So we'll call this the previous condition. Right? What's going on initially, right? Happening at the beginning. And at the beginning, we're told that we have a tension force of 48 newtons. Let me double check that value to make sure we're correct. Yes. We're told that we are moving at a velocity of 32.17 meters per second, and we are swinging this with a radius of 3.3 meters. Now this is going to give us enough information to solve for that unknown mass. We're going to use that, plug it back in to find our breaking tension, if you will. So, remember, our tension force is a centripetal force, so we can set it equal to mv squared over r. But this is just our centripetal force, right? So I'm going to try to rearrange our equation to get mass by itself. So if I want to get mass alone, I can multiply by the radius on both sides of our equation. We'll get this value over here to cancel out. And divide by the velocity squared, okay, on both sides of our equation. That will cancel out on the right-hand side. And that will leave us with an equation that can express just our mass value. Okay, and the mass will be equal to our radius times our tension force divided by the velocity squared. So here's what we'll do. We're going to plug in these values and use those to solve for our mass. So here we go. Mass is equal to our radius, 3.3 meters, times our tension force, which was 48 newtons up here, divided by our velocity squared, which was 32.17 meters per second squared. Don't forget that value. That's an easy mistake to make. So 3.3 meters times 48 newtons divided by 32.17 meters per second squared. Sorry. That's going to end us with a mass equivalent to 0.153 kilograms. We'll just round to 3 significant figures here. Now, as we mentioned at the beginning of the problem, mass isn't going to change. And so the mass we start with is going to be the mass that we end with. So now I'm going to take this value and bring it back to our braking scenario, right? Now that we have our mass, 0.153 kilograms, we can solve for what's our braking tension. And a good way to check this is that we know it should be larger than our tension at the beginning. It should be bigger than 48. Okay? So let's plug in the values that we know. Remember, our tension force is our centripetal force, so it's equal to mv squared over r. This is our FC, right? So now we'll plug in our new mass. Well, not new, but the new to us, because we've just found it. 0.153 kilograms times our velocity squared, 59.1 meters per second squared, divided by our radius, 0.717 meters. And as we mentioned earlier, it should give us a value for tension that's higher than we began with. So 0.153 times 59.1 squared, don't forget that, divided by 0.717. So that's going to give us a new value for our tension force. And I calculated that to be about 745.6 newtons. So we double check with our key, right at 745.6 newtons, which again, it's much higher than our initial tension, okay, which is going to therefore cause our string to break. Okay? So in this problem, remember, okay, that we can change the radius of that circle, we can change the velocity of that circle, but we're not necessarily changing the mass. That's the one variable that's staying constant in the previous condition as well as in the braking condition. Okay? So hopefully this will get us started kind of working through this problem number 5. Okay? Good luck.